is 14 over 10. No. 7 over 10 plus 7 over 10 is 14 over 10.
Yeah, you're right.
Over 2 is 7 over 10. Right? Or 14 over 20, then, yes. Either way. Okay, so that would be, whatever that number is, will be your answer. How much is that, approximately? 111 plus, actually 111 minus 23/8 minus 1.4 is whatever that is. Minus 1.4. Looks like you get 106.7. So that would be, does that sound reasonable? Look at the table. Does that look like a reasonable number? Are you comfortable with that answer? Well, the temperature index at 9460 is 111 degrees, but you are a degree lower and 2% less humidity, so you're about 4 degrees less than the 111. That seems reasonable, doesn't it? I think that's, again, if we were way off, if we got a number larger than 111, or maybe if we got an answer of 93 or something, that would have been ridiculous, right? And you would have noticed that. But this number looks reasonable. Okay. Let's see. We need to do a few of these applications of derivatives, second derivative test, and all that business. Let's look at 16 is asking you to do this problem using Lagrange and the second derivative test, so that would be a good problem, I think. Let's look at this. It says the temperature in an enclosed chamber is given by where X, Y, and Z are all positive. All right, so X, Y, Z is all positive. So that would be in the first octet. Cold object with shape 32, Z equals 32 over X, Y. So this would be an object, Z equals 32 over X, Y. Is placed in the chamber and allowed to reach an equilibrium. At what point of the object is the temperature a min? So we want the point where the temperature is min, or just big T. Big T is min. Okay. Use Lagrange and the second derivative test. So you have to do it both ways. How are you going to do it? Which one do you want to do first? We could do the second derivative test first, maybe. So what would you do if we were doing by the second derivative test? What would you? First we have to get what? Well, first you have to do what? The first thing you have to do is get a function of how many variables? 2. So what would T of X, Y be? (64) over Y plus now you have a function of 2 variables. For second derivative test, you must have a function of 2 variables. We don't know how to take it as second derivative test with a function of 3 or more variables, so we have to do it this way. All right, so now, what was the next thing you have to do? we have this. What do you need to do now?
Partials of x and y.
Yes, t sub x. What is t sub x?
Y is 60 minus 64 over x squared.
Set it equal to
0.
and then t sub y is
Same thing but y.
and now
Solve the system.
how are we going to get critical points? Remember, you get a system of nonlinear equations. So what would be a good way to get
Put x and y on the opposite side of the equation.
You solve the first one for y and plug it in the second one.
Sure, you could do that in this case. So if you did such a thing, what would that yield? So you'd solve for y here, and then you'd plug it into here. What would that give you downstairs here? X minus 64 over what? X minus 6 over y squared. So this would be squared, wouldn't it? Solving for y here, so that has to be squared. And that's equal to 0. So how are you going to get an x out of that? Yeah. We need, so that's going to give me x minus, all right, if we take this, if we square it and take its reciprocal, what would that give us? X to the 4th over
Should be 64. Right?
64. Okay, well, what would x be? It is, isn't it? Isn't it 4? So x equals 4 here. And if x is equal to 4, then what is y?
Couldn't x equal 0 there too?
No, because it said all the x, y, and z is positive.
Oh, well.
So, and x couldn't be 0 anyway. Well, technically that would be a point of, this would be, but again, notice that x equals 0 isn't even in the domain of this. So x could not be 0 under any circumstances. It's not even in the domain of the function.
Y equals 4.
So y would equal 4 as well, wouldn't it? Okay. So the only critical point we got was the point 4, 4 something. Well, if x and y were both 4, then what would z be?
2.
2. So this is the only critical point we got. Now you want to prove that that is a min, don't you? By the second derivative tests. So how would you prove that's a min by the second derivative test? If it's a min, then we would want what kind of concavity?
Okay, well.
Concave up, wouldn't we? We'd want, so that would mean that the second derivative would have to be what? We'd want positive, wouldn't we? Okay. All right, so what should you do now? TXX. What is TXX?
64 over x cubed.
Almost. How much? One more time. This is minus 64 x to the minus 2.
Oh, it's 128.
128 over x cubed, isn't it? But that's evaluated at x equals 4, so that would be 2. Okay, what's TYY?
Same thing.
Isn't it the same thing? 128 with a y in it. Evaluated at y equals 4 would be 2 again. And then you want TXY, don't you?
Should be 1.
That would just be 1, wouldn't it? So what do you do now?
So we txx times tyy minus txy squared.
Yes, the TXX TYY minus TXY squared is equal to
3.
3, which is positive. What if you'd gotten a negative number here? What would that have meant?
Saddle max.
No,
Saddle point delta.
saddle point, right? So we want this to be positive, but we also want what else? We also know that TXX and TYY are also positive, so what does that mean? Concave, right? So, min. So you've just verified. Both of these are positive as well, so the whole second derivative was positive, which means you're concave up, so you have a min. Because it's the only critical point and you're concave up there, it must be the absolute min, right? What about the Lagrange version of that? I wanted you to solve it using Lagrange as well. How would you phrase that problem in terms of Lagrange multipliers? Remember, all of those problems are phrased, extremize something subject to something. Yes? So this is saying extremize this t of x, y, z subject to what?
The object
Yes, and how would I write that here?
for this type of
Let's
question.
say like g of x, y, z equals what?
32 words, right?
Right? You have to get it in terms of all the variables. So extremize a function of 3 variables subject to another function of 3 variables equals a constant. That's the way those problems always have to be structured. Now the Lagrange tells you to do what?
Has a constraint.
This is the constraint, that's right. This is the constraint.
Del T equals lambda del T.
Yes, there you go. Del T, the gradients are scalar multiples, are parallel, right? Because remember, this surface and this surface are touching somewhere, so therefore the tangent here yields a normal vector this way and a normal vector this way. So this del T and this del G are scalar multiples, aren't they? All right? They may or may not be going in the same direction, it doesn't matter. But whatever it is, they are parallel, so therefore they are scalar multiples at that point. So this would be this critical point here. If these are smooth surfaces, then that would happen. That's what we care about. All right, so what would you do now? We want t sub x equals lambda g sub x. What was t sub x again?
Y minus 64 over